Welcome everybody, and thanks for joining us today for this webinar. We will be discussing how to model simultaneously multi-trait and multi-environment structures with ASReml-R. Dr. Salvador Gezan will be presenting this webinar. If you have any questions for Salvador, please ask them in the Q&A section. We will attempt to answer these live, or if there isn't enough time, we will answer them in a follow-up email along with the recording. All right, so without further ado, I will now hand you over to Salvador.
Good morning, good afternoon. Let me just get ready by moving a few things away. So hello everybody. I'm glad to be here and to show a few more things. The original idea of this webinar came from some people asking around support. Can I fit a multi-trait and a multi-environmental model with ASReml? And the answer is yes, but it's not an easy thing. And also some people come and ask, can I also incorporate some spatial analysis into a multi-trait or a multi-environment analysis? And the answer is yes, but it's not easy. So I will be trying to give you a little bit of a flavor of how these things are working. This webinar will be a bit more difficult for the majority of you because I'm going to build them into previous explanations that I have done in other webinars for multi-trait analysis and for multi-environment. Now, if you're familiar with those things, it shouldn't be too difficult to understand the extension. If you're not, I recommend you to go a little bit to the older webinars, understand those topics, and come back here and again mature these topics. The data set and the code will be available, and then you also have access to this video later too as we finish. So let me just get started. We do deal with our complex linear mixed models with different fixed effects and random effects. And we combine them to do the typical, what I call the one universe or the one dimension, if you want, where we deal with the spatial analysis. So we make the error structure a little bit more complicated with correlations and so on. Usually, because we deal with field trials, we have this double correlation on rows and columns. We also deal with the multi-environmental trials analysis, which is also sort of like a second dimension. It's not just one site, it's several sites all together and combined, which brings the complexity of having to model G by E, and usually the G by E, we model it by some sort of a US structure or a complex structure with variance covariances between environments and different variances within environment. We also deal with this universe on multi-trait analysis, where we combine several traits, and then we have the same genotype. It's going to have breeding values or genetic values correlated across the traits, but also the residuals happen to be correlated because it's the same experimental unit measure for all the traits. So you can see here, it's not really one dimension, it's one type of universe, the one that we are more used to kind of deal with. But then when we go to this multiverse, and that's where I put the Rick and Morty figure there, we are trying to kind of expand this from this, our understanding of these usually 2 dimensions to something that is 3 dimensions. And it becomes a bit more complicated. Because now, for example, when we deal with multi-trait and multi-environment, we do have a genotype, breeding value from one genotype is going to be correlated on trait 1 with the breeding value of the same genotype on trait 2. But wait, on trait 2 in environment 1, and on trait 2 in environment 2, and on trait 1 in environment 3. So now you have this combination of correlations between environment and trait that makes everything difficult. On top of that, we have that the errors, some of the errors are correlated. Yes, the same experimental unit, it will be a same experimental unit measure across several traits, but that experimental unit is independent from another experimental unit in another trial, which actually is correlated with the traits that are being measured in the other trial. So again, that's where you think that happens. I'm not going to go to the other ones about multi-trait on spatial analysis. and multi-trait, multi-environment with a spatial analysis. Again, we are just bringing all those things. And again, it's always very hard to visualize these things. I talked about multi-trait before, the relevance of using the multi-trait where we combine the traits into several analyses. The key thing you have to remember is that there's correlation between the traits that we model as correlation on the genetic effects across the trait because the similar alleles are affecting all the traits. Again, remember, it's important to consider a multi-trait. The experimental units are correlated too. So we have to model the correlation both in the G part, which is in the random part, and also in the residual part, or what I call the R part, okay? So that's one thing. In multi-environmental trial analysis, where we combine several trials, we have correlation that comes through the same genotype present in different environments. Some people think that different environments can be treated as different traits, and that's fine. So we're going to have that multiple correlation of genotype and environments, and the differences on those correlations not being exactly one is what we know as a genotype by environment. But in this particular case, the experimental units are going to be independent, okay? Because it's not the same plot or the same plant in one environment than the other environment and the other one. And physically, they are very far apart. So we have to think about this multidimensional linear mixed model on both of those contexts. And we can think that we have vectors that are a stack of maybe the same, maybe this is one environment on one trait, maybe this is another trait for a different environment, maybe the same environment, different traits, different environments, all those combinations. So obviously we're going to have a set of fixed effect for each of those dimensions, if we think about dimensions. And then obviously we're going to have breeding values for those different dimensions. Again, think about dimension trait 1 and environment 1 and trait 3 and environment 3, for example. And the residual terms also goes with the same direction. So what is key on all of these analysis is that we need to model for these two dimensions. We need to specify in our linear mixed model that there is a variance for the first dimension, a variance for the second dimension, and then we have a covariance, which in this case is for the genetic effects or the genetic correlation between traits or environment or so on, that needs to be modeled. And this usually is a US structure, like is shown here, or sometimes we model this, which is a bit more typical, as a CORGH or a correlation structure where we have the diagonal on the side. And also we can expand that to be more like a factor analytic. So if you're familiar with factor analytic, we decompose this into loadings and specific variances. Okay, so the key, and these are a couple of examples, is that we want to model that correlation between different environments or between different traits or both. As you can see here, what the CORGH is just to give you an idea. Variances associated with each of these dimensions and correlations between the first and the second dimension, first and third, first and fourth, and so on. This is very demanding. It's 10 variance components for 4 dimensions that we want to calculate. And then ASReml is very able to handle 4, 5, 6. As you get with much more dimensions, many more dimensions, you start having to use a few tricks and assist ASReml. So that's what I want to try to show you. And I'll come back a little bit to the factor analytic to give you a bit more of ideas on this, okay? So I want to show you directly the data sets that I have and an example. So this is very practical in this sense. So let's see, we have enough room for all of that. So I'm going to start with a multi-environment, multi-trait analysis. And this is a data set. Let me just run a few things. I'm going to obviously use ASReml. This is a particular subset of a data set on which we have 4 environments for 95 genotypes that were measured for 3 traits. So 4 times 3 gives me my 12 dimensions. And obviously I'm interested in combining all this data, and you're probably very aware the multi-trait analysis gives you an increased accuracy, and obviously we have multi-environments, so we want to combine different environments and evaluate the correlations and so on, and rank genotypes across environment using this multi-trait analysis. By the way, there's a lot of ways to do this with some of the Bayesian approaches, and you have different libraries that do it. I'm just obviously going to follow the the frequentist approach in this particular case using ASReml and all the context of REML, okay? So I'm using these 4 environments by 3 traits, that's 12 dimensions. I have my 3 traits are ear height, plant height, and moisture. This is a maze data set. I'm not using pedigree, not using anything else. This is a subset of this data from this manuscript and that we found in the library Agridat. So I'm going to read this subset of the data. It is done in a way that the sites or locations in this case are stacked down, and also we have the replicates effect, which is the only design effect that we have in this particular analysis, and that's pretty much it. So, and again. So this is just a little bit of the observations. One thing that is very important that I'm identifying here is the ID, or this is an ID for the experimental unit. So this is the same plant measured from that, and it's unique for each of those plants or plots, okay? So just a few elements that are always important to see. Do I have each of these genotypes located in all the sites for connectivity, thinking about an MET? The majority of the genotypes are in all locations. Some of them are in more, some of them are in less, and some of them are in all 4. So that's part of the unbalance of these experiments. I'm just looking at a couple of things that you're always good to look at. What is the exploring the data? How is the correlation between the phenotypic correlation between traits and so on? By the way, if you are interested in the data, we'll have the data available for you with the code and so on. So just keep that in mind, okay? Now, histogram to see some distribution, to look for outliers, you have to kind of like explore the data. In this case, will be by trait, by environment. So some data preparation, just making some of those factors, some of those elements as factors, so location, genotype, and so on. And what I'm going to start is with a little bit of an easier way. I'm going to start with one site to do a multi-trait. Okay, so I'm going to filter for the location PR. This data set obviously is much smaller. It's only 248 of the total observations. I do a calculation because I'm thinking of a multi-trait, I'm going to do a calculation of a summary. And the thing I'm looking here is at the means of the traits. So this is 7112, the mean is 9.8 and 198. So you see they have different scales, and that might bring problems with some of the variance components, okay? So I'll come back to it, but it might seem like appropriate to multiply, for example, moisture by 100% and you bring everything into the same scale. But it's always a good practice to help the system, in this case, the REML, to iterate well and to not get lost somewhere. So I'm going to fit the following multi-trait model. The basic univariate model has an overall mean, a replicate effect, which is fixed, and then a genotype that is going to be random because I'm interested in the correlations and the variances and so on. So I'm going to fit this model. ASReml works, if you don't remember too much, works where you put a C-vine for the different traits. So I have ear height, moisture, and plant height. So it's stacking down the vectors of the traits. There is a reserve word for trait, which allows me to have a unique mean by trait. The trait is going to identify these stacked down vectors. Then I have rep, which is my only fixed effect, nested within trait. So that's a fixed effect. I'm considering rep as a fixed effect. And then I have the main random effect, which is these nested effects of genotype within trait. It doesn't matter the order. But you can see here that I'm saying that the traits are going to be modeled. Remember, this is a 3x3 matrix. It's going to model with variances in the diagonal and correlations or correlations on the off diagonal. So 3 correlations and 3 covariances, because in this case it's 3x3. And that's going to model the correlation between traits. I need to specify that the residuals are non-independent because it's the same experimental unit measure for the three things. Like you can see here, the same experimental unit measure for those three responses. So I'm specifying a similar structure, CORGH. Now, in this case, is the unit. So every experimental unit is defined by three elements that are correlated. In this case, I'm saying every genotype, which is much fewer levels, it's defined by three elements or three levels, okay? So I'm just going to fit this, providing some starting values to help the system. It seems to have converged. I have a plot, and the plot looks, again, looks a little bit strange, and this is because of the scale of the moisture is very narrow, so the residuals are very narrow. They don't move between -20 and +20, as happens with some of the other traits. But we're going to live without it. Still, the system is relatively good. And you can see here the correlations between the different traits. Moisture and ear height is 0.51. Plant height and ear height is 0.1, and then it's -0.33. Significance for most of them. And then we have also the residual correlations here, which follow a different pattern. So very happy with this analysis. Obviously, we could find some outliers. We can look at some of the distribution and decide to eliminate some extreme observations and so on. But I'm just going to leave it there for this part. Now, just want to show you that we can approximate this CORGH with a factor analytic, which is very handy when we have a lot of more dimensions than 3. And this is used for multi-environmental trial analysis and for multi-trait. Just very briefly, the factor analytic model, it's another parameterization and approximates this 4x4 matrix, a matrix with dimensions 4x4, by using the compositions of loadings and specific variances. The advantage of this is that it takes fewer variance components to approximate that 4x4 matrix. You can add more loadings, which is adding more components to the factor analytic, and then you end up with more variance components that tend to approximate better to the G matrix. Again, I'm not going too much into details. Just trust me here that what I'm saying is that the factor analytic is a good way to approximate this CORGH matrix that we are calculating, okay? So I'm going to do the same thing here. I just changed CORGH to factor analytic. It's one dimension. The log likelihood, it's a little bit different. 1284, 685, 1286, 362. Again, it's an approximation. The plots are going to be very similar, and the variance components are not very informative because they are done into the specific variances and the loadings for the first dimension. But you can transform that, and again, trust me here, I'm extracting the variance components and calculating that psi matrix and calculating the lambda matrix, doing the proper multiplication to get the variance covariance matrix, and I'm getting the covariance to correlation of that matrix, which gives me a correlation of -0.51 between trait 1 and trait 2, which is very similar to this -0.51. Then the second one was estimated as to be 0.1, and in this case is estimated to be -0.15, so a little bit different. And then the third one is -0.30, and this is 0.33. Again, the second one is very variable, in part because of that scaling, but also it has a large standard error. So it's converging to a slightly different value, okay? So it's very likely that that trait is uncorrelated with the other trait. So how do I extend this model that has three traits to having 3 traits times 4 environments or locations? And it is different ways that you can think about it. You can say, well, I'll just read the whole data, and I'm just doing an hypothetical case here, y1, y2, y3. I have my traits, so a mean for each of the traits. In this case, it's going to be across all the 4 locations. I have a mean by location. Let me undo this, edit, undo. So I have a mean or an effect of location within trait, because I have lots of locations within trait. I have a rep nested within location within trait. It makes sense. But once I start getting into the random components, it looks a little bit strange. You will say, why I don't just extend my gen correlation trait to add correlation GH location? Because now I have a matrix of dimension of number of genotypes by genotypes, but this matrix is 3 by 3. The Kronecker product of this matrix is defining the variance component is defined by a 3 by 3, as I just showed you here, times 1 to 5 by 4 by 4, which is going to give you this 12 by 12 matrix once you do the Kronecker product. So it makes sense, but there is a catch with this. First, these two correlation matrices are defining variances. And you cannot have variances in both of them because the system is not defined. So you almost have to eliminate one of these H's on one of them and say, oh, I don't want heterogeneous variances by trait. But that means there's a common variance by location, so it doesn't make too much sense. So I leave it there and I eliminate the variances on location, but that's saying almost that all the genetic variances are the same across all the locations for one trait and all the same for another location. So it's not giving me the flexibility that I need, okay, to define different genetic variances by combination of location trait. But there is a trick for it. And something similar happens with the residual terms. It's not only going to be complex, but I want you to understand a little bit what happens here. I'm asking, with the direct sum, I'm asking for a different system of 3 by 3 by location. And that makes a lot of sense. So what you have here is you have a 3 by 3 matrix of correlations for the 3 traits. And when you put the slash location, you say that is going to be applying for location 1, for location 2, for location 3, and location 4. Fine. And you'd have these ID units because this 3 by 3 is affecting each of those experimental units that you have in each of those locations. So that one is fine. It's complex to understand, but that one is fine. So what is the trick on this? The trick on this is creating a new factor and changing the structure of the data set in order to be able to answer this fit a model that will do these things. So I'm going to read the new data set. This is mice MTME. And what I have done in this particular case is, remember we have the 3 traits to the side. Well, and then I had this replicated 4 times for each. Now I'm going to put the vectors, the actual traits, one on top of the other that already were on top of each other from the locations. So I need to create one variable here, which is I call var, which has all the records of the variable ear height. Then when you go to the end of a data set, you have all the records from plant height. So I have ear height, moisture, and plant height. And within each of these, I have location 1, 2, 3, 4, 1, 2, 3, 4. That's all fine. So, but what do I need on top of that is, notice that the response variable, I just call it response. And I also have the IDE, which is the experimental unit. So I'm going to show you a little bit how it happens with this data. If I sort this by IDE, you will see that the same plant or plot has these 3 records, which are the responses for ear height, moisture, and plant height. And this happens to be on location PA. Okay, and so on. So this is very important because I identify each experimental unit in a unique way. And this ID is just a unique code. Okay, so that's really the structure. Now, if I manage to combine the name variable with location, I have 3 variables with 4 locations. I'll have 12 levels, and I'm going to call that group. And that is the key that I need to solve all these issues on the analysis. And again, this is what it makes it a little bit complicated. So I can do some exploratory data analysis. This is very similar to looking how many observations I have per environment per trait. You obviously need to have enough observations. And this is again looking how many observations do I have across all the traits and all the locations, some summarization tables. So this is not very relevant. But what is relevant is this variable that I call here group, which is concatenating or pasting the combination of variable with location. And I can show you here that I concatenate the groups and the levels are ear height BA, ear height GR, A height, and I have 12 groups. So now what I'm doing is I'm thinking, hey, I have this 12 by 12 matrix of variances and covariances or variances and correlations, which is going to be, let's think about this. This might be the set of correlations that exist across all locations for trade 1. This is the set of variances and correlations that occurs across all locations on trade 2. And these will be the covariances or correlations between trade 1 and trade 2 through different locations. Now that is the matrix I really want, okay? So in order to fit that model, first I need to sort the data, and it has to be sorted in a specific way. So I have to try this, but you can check this. And then I need to, as I said, I need to treat the traits, in this case, as an additional location. And you have to be a bit careful with the independence because some of the observations are independent and some are not. So let's go and just try to understand what the model is doing. Now, this is a one-dimension analysis because it's only one response, but internally we're fooling ASReml in one way. It's like it's actually not one dimension, it's 12 dimensions, or if you think about three traits, okay? So I have a group effect, which is equivalent to the mean of trait, but this is the mean of a combination of trait and environment. And then I have a rep effect, which is not going to be the same for environment 1, environment 2, trait 1, trait 2. So it has to be done by group. And then I have this genotype FA group. So remember, group is a 12 by 12. So this is going to define a 12 by 12 variance covariance matrix by genotype. Perfect. That's exactly what I want. And I have defined the error structure in the same way I showed before. It's independent by location, but within location, we have a 3 by 3 matrix defined by CORGH bar. The number of levels of bar is 3. So this is a 3 by 3 matrix defined across all the experimental units done by location. So let's just run this model. It does complain. I didn't provide any starting values. It does complain a little bit. If you fit a few more times, eventually ASReml will say, oh, we have converge, or we almost have converge, okay? We have a little bit of instability, but we can explore that. Now, when we look at the plots, I'm not going to show you the plots because the plots are combining all the variables into the same graph, and then it doesn't make any sense. So all the residual part, you have to do it beforehand. So let me just show you one of the graphs. It looks very weird. You see all these observations. That's moisture. Then the other ones are the other two traits, because it's thinking that you want to plot things by location. But actually within location, because I'm filling up the system, I have 3 different traits. So ignore those. Now let's see the variance components that I have. And there's a couple of things that are interesting. We have the factor analytic of order 2, which I fitted here. The factor analytic of order 2 that has the 12 specific variances that you see here, because it's a 12 by 12 matrix, the 12 loadings from the first order, and the 12 loadings from the second order. Okay, fine. That's are going to help me to construct the 12 by 12 matrix. Now, there is some things that are interesting later. I mean, these are the variances. These are for a third loading. I have also specific variances for a third loading. Sorry, I forgot I fit orders 3 factor analytic. But I like this one because this one, notice that it says BA all the way to BA. So this is fitting a block diagonal matrix of residuals by location. These are the correlations, or the residual correlations between trait moisture and ear height, plant height, and ear height, plant height, and moisture on terms of the residuals, and the specific residual variances for each of them. Now, location 1 has a different set than location 2, a different set than location 3, and a different set than location 4. So exactly what I really want. So now the nice thing about this is that I get pretty much everything I need. So I'm going to start pulling up the loadings from the factor analytic, the specific variances, and I'm going to provide you, I can show you the variance matrix, variance covariance matrix, which is constructed here, not very easy to see. More relevant is that I show you the correlation matrix. Now, again, it's too big to see, but you see once in the diagonal, and then you see this 0.94, 92, 90, 69. Notice that now they drop because this 4 is the same trait, is the correlation across environments on the same trait. It's very high, almost 1, higher than 0.9. So that means there's little G by E on ear height across these environments. But this is the trait-to-trait correlation between one environment and the other environment. They all seem to be somewhere between 0.5 and 0.6. There's a few 0.4 here. And then again, you have, this is the correlation between plant height and ear height on that set. So much better than looking at that way, we can use sort of like a heat map. I'm using ASR Genomics to show you that. And I'm going to make this a little bit bigger, probably all the way up. You can see here the structure, 4 by 4, 4 by 4. This is the plant height. So within the traits are very good. And across the traits, some of them are better than others. Some of them are actually possibly with some negative values, which makes sense. Okay, obviously we need to explore this in more detail, but it's giving me the right structure that I was expecting for these traits. And I have the correlations too. So now I can proceed to get predictions. Now for ASReml, predictions are going to be very simple because, let me just show you the data frame. I ask prediction for the combination of group genotype. It's going to give me for each of these 12 groups and for each of the genotypes, their performance. You have to be careful that obviously this is ear height, this is moisture, completely different scales, completely different things. If I was interested on the means across the 4 locations, then I need to ask ASReml to consider just the mean of the first 4 observations for that genotype. So I will give it a weight of 1, 4, 1, 4, 1, 4, and 1/4, and the rest I'll make them 0. So that's very doable in ASReml, and this is exactly what I did here. So I want for the group, for the level group, use the following weights, and then collapse and give me the mean by genotype. And you can see here, this is for ear height. I see the predictions for genotype. They make sense. This is 80, 91. The full data here, the average of these 4, it's around 80, so it makes sense. And the average of moisture is around 12. And then when you look at that, you get a mean of 12, more or less 12 for that genotype. Okay, so this is one way to fit this multi-trait, multi-environment. There's a lot of, if you have more terms and more things, you can add those. This is a good moment for a couple of short questions.
Yes, Salvador, we have a couple of questions actually. So one question would be, do we need a minimum correlation between traits to use a multi-trait modeling?
No, you don't need a minimum correlation. It will be estimated. It will be estimated as 0 if you don't have any correlation. I mean, that's part of your question. So no. Now, what you do need is you need individuals, in this case, genotypes that are measuring more than one trait and measuring more than one location in order to estimate those correlations.
Thank you. And when a same trait is collected multiple times in the same field, can this be considered a multi-environmental trial?
Well, actually, that would be more like a multi-trait. So can you repeat the question? I lost the last bit.
Yes. When the same trait is collected multiple times in the same field, do we consider this multi-environmental trial?
Well, actually, that would be a multi-trait data. So it'll be the same thing as ear height on harvest 1, ear height on harvest 2, harvest 3, and harvest 4, for example. So it's a time 1, 2, 3, 4, so you can treat repeated measures as a multi-trait analysis. Remember, the experimental unit is the same that is being observed 4 times, which means it has to be correlated. So the residual part needs to be modeled that way. A good question.
Thank you.
Okay, so one more thing I want to show you, and this is a little bit of an extension of this multiverse. And I know there's probably a lot more questions, and happy to answer them at the end. And also, I'll try to provide, if you leave them in there, I'll provide more answers in a document that we'll distribute to, or you can send me an email later too, okay? So I know it's a bit difficult to have all of that. So what I'm going to show you just is a little bit of an extension where I have a spatial analysis in a multi-trait analysis. And I want to bring, I'm going to do it relatively quickly, but I want to bring a slightly different thought, or why some of these things are not very straightforward when you want to start combining some spatial analysis and some other things. One of the difficulties we have when we do spatial analysis is that we are modeling correlation on the residual part across rows and across columns. But if you add another dimension, which is, I want to do that for traits, for 2 traits, not just 1, well, the correlation of the residuals, can be modeled with a CORGH, but what happens with the correlations of the spatial correlations? They are going to be correlated. Think, for example, you're measuring total height and ear height. They are highly correlated on the residuals, positively correlated. So the spatial correlation for one will be similar to the spatial correlation for the other. But that means there's no model, there's no actually, I will say there's no distribution that defines a CORGH for correlations. It's not very clear. So there's no really theory for that. But one way we can do that is we can move the analysis of the spatial correlation from the residual part to the actual G part, from the random part. So I'm just going to analyze one trait. It's one site, 427 genotypes. Remember, one site, and it has 2 traits that I want to spatially kind of correlate. This is an augmented design. I'm just going to make some factors random. This is how the design looks. It has some spatial patterns. You can see the locations of the checks. There is a group of checks in here. And then there is a proportion of 16.2 checks, and there's some names of the checks. And just for sanity, to look at the variance components, I'm going to divide the weights by 100. So don't worry about it. I need to sort the data in order to fit this. And then I'm going to fit a model that has a nugget effect, a row effect, because I have a trend. Row is a random effect. So I do have a trend on the field. And then this is autoregressive. This is for one of the traits. We have some residual plots that look okay, and some variance components that seem reasonable. And there's some strong spatial correlation in one dimension. Okay, the other one didn't have, it was not significant, so I drop it. For the other trait, we might have something very similar. Before moving, notice that I have the units here and the spatial correlation on the residual part. You get exactly the same model if you move this from the residual part to the random part. So this is what I did. I put it into the random part. You can almost see this as this part. And now the units happens to be moved to the residual part, and that is going to be the nugget. Okay, so when I fit this model, I get very similar log likelihood values. I have quite a bit of warnings because there's not much information for the nugget on this particular data set. But 179, 78, 20, it's very similar to the 178, 78, 79, 78, 20. So it's the same analysis. The The variance components are going to be also the same. The correlation is 0.83, and we have this specific spatial variance, and we have this nugget variance. Fine, I'm happy with this model. I have moved it, and then you can think about what happens with the other traits and something similar. So now, how do I think about this multi-trait analysis? Now I'm going to combine weight and stem, and I do it in this particular way called C-bind, as I showed you earlier. I have a mean for trait. If I have reps, I will add reps. And then I have this CORGH trait variety, which is going to give me a correlation between the two traits, variances for the two traits, and then the variety. So very similar to the other multi-trait model, just we have two traits instead of three. And I have this spatial component that I add, which is a row effect, which actually are correlated because obviously, if these two traits are correlated, that means some of the design effects are also going to be correlated, some of the trends are going to be correlated, and so on. And then I have my units, and then this CORGH trait, which is going to correlate the residual terms. So really very similar to the previous models that I showed before. I'm not going to fit this one, but now I want to add the spatial component. And I say, well, if I'm going to add the spatial component into the error part, I can replace the units by this, which is going to model correlations on the residual part. But wait, that's not going to be correct because it's going to say your correlations on the row is 0.6, but that applies to both traits. And you don't want that because maybe that for one trait is 0.6, for the other is not 0.6. It has a completely different dynamic. So this sort of model that you fit here, even if it converges, is going to give you some things that are weird because the spatial is not being described, it's not describing the spatial correlation by trait. Okay, so the key on this is to move the spatial correlation back to the G part, which is what you see here. I have moved it to this element. So I have actually, yes, I have a trait one, air one, and I should put an air one V here because it's a variance associated with this, and there's a variance associated with that set. Notice that in this particular case, I'm saying, give me the spatial error on the G part, but give it to me just for trait one. And then here I'm saying, just give me that just for trait two. Okay, so they are independent. They're going to act on one trait or in the other. So I'm not correlating them. I'm still assuming these are independent units, which is not completely correct because, as I said, maybe the correlation, the spatial correlation on one trait correlates with the spatial correlation on the other trait. But at least I'm not doing this awful thing, which is saying both traits have exactly the same correlation. Okay, so this model is really incorrect. This model gets a bit closer, but it's still not describing totally, but I think it does the solution. So let me fit it. There is something I didn't like from me. I think is, it's asking, I think it's this B that I put here because let's see what we get. Yeah. So there sometimes it becomes a bit temperamental, okay? It needs a few more iterations and so on. But let me just show you what happens with the output. And again, this is a bit more complicated because we have variety. So this is the correlation between weight and number of stems. It's very high, almost 1, and actually has a relatively large standard error, really. Okay, so it's been estimated with a few things. By the way, don't trust totally this fit because I'm not providing starting values and I'm asking a lot. So I should probably get a bit slower with the starting values and so on. But I just want to show you what logic you can use, okay? Now, the other thing that happens with this data set is unreplicated trials. So there's difficulty on estimating some of the components, okay? So the only ones that are replicated are the checks. So then you have to revisit a little bit more. So, but this is a genetic correlation between this is between rows, sorry. This is between row effects, and this is between row effects. So this is spatial correction. The one here, trait variety, is the genetic correlation between the two traits. So this is minus 0.10 with their specific variances. Not very high, but something like that. This actually makes sense, has a large standard error because there's not much information. Now, what is this? This is the specific one for high. These two lines are describing the autoregressive errors for trait 1. And you can see here that this is the variance and this is the correlation. The variance is almost 0, okay? So maybe there is no spatial term in there. And for the second trait, you see this one here. Actually, their things seem a bit more interesting. This is the correlation on rows for trait 2. This is the correlation on columns for trait 2. They seem to be significant. And this is the spatial correlation. On top of that, I have this bottom part here for the residuals, which is the residual correlation, so this minus 0.01, which is almost 0, between the residuals on the same experimental unit. So this is the unit for experimental unit, and then on the traits with their specific residual variances. So I'm very happy with this model. It still needs a little bit more tweaking, the converge well. It's reasonable that has a huge standard error, again, because there's not much information. So I need to drop a few things. So what I'm going to drop is I'm going to drop the spatial correlations between for trait 1. So it's the model I have here at the end. But before I go there, and I don't have, I have plenty of time, I was thinking, is there any way I can correlate these residual terms between the different auto errors on one and error on the other? And again, you're going to run into the same problem as before. I'm going to estimate a variance, a spatial variance by trait, that's fine. And I'm going to estimate a correlation between the traits on the residual errors. But once more, these matrices are going to define correlations that are unique on rows and columns that apply to both traits. So I'm not solving the problem with this analysis. So the best sort of approach is to say, let's assume these spatial correlations that are acting independently from the two traits. It's not totally correct, but it allows me to combine all of this. So let me run this model. And this is the model that I call, I'm okay with this, I like it. And actually I do have also this row term here. And let's see some of the output. I still have this huge correlation here. Now I have the spatial correlations for trait 2. And then I have some genetic correlation of minus 0.10 and so on. So I can proceed to get my predictions, which in this case will be the predictions of weight and stem with their spatial correlations and so on. So that's what I can do here. And I can get my predictions for each of these genotypes or varieties for each of the traits, and then I can combine them. There's one thing that some people tend to ask, and I saw the question somewhere here. Why don't I just do a two-stage analysis? And on the first stage, I get the corrected means for weight, and then on this, and then I get it for stem, and I apply for each of those traits their spatial correlations, and I get my means, and then I correlate those into a bivariate analysis. It makes a lot of sense. You save energy and so on. But notice that the residual is going to be incorrect. In this residual, I'm correlating the same experimental unit that has the several traits being measured. But when you do a two-stage analysis, you get means. And then you're saying, oh, I'm going to correlate these means. But wait, those means represent several experimental units in your experiment. In this case, it's unreplicated, so not very likely. But if you have replicated, it represents an adjusted mean across several experimental units, which in turn, it means that that correlation that you're estimating is not the correlation from the true experimental units is the correlation from your adjusted means, or your means from the first stage. Now, I'm not totally aware statistically what are the consequences, and in practice, what are the consequences of the selection, but statistically, it means that you're correlating things that are more likely to be independent because it's averages across experimental units. So what is the solution? I'm not going to give you the solution. You have to think about what could be the solution, but the software allows you to explore these things and allows you to expand your options of models and see what it works for you. Now, can I add to this multi-trait spatial analysis, can I add multiple environments without going through a 1, 2, or 3 stage? The answer is yes, but it's not going to be easy. Okay, you can do the same trick of stacking down the different traits and defining the locations and creating the group variable. And this is what I have done here. Response group, you're going to have the same as before. It could be 3 traits and 4 environments. You have your genetic effect, but you might have some, like in this particular case, I might have a row effect that are correlated by variable. But the thing that is going to happen is that you're going to have to define independent spatial corrections by group, where group is this combination of trait environment, which is fine. And then you can define your residual term as correlated by location, which is what we did before. So the main message on this section is that you can move some of the things from the spatial analysis. You can move it from being on the residual into the G part, and it brings you a few additional possibilities, okay? However, don't forget that that means we are adding a nugget, because in one sense, this residual, it's part of the nugget, okay? Just to not use all my time, I wanted to explain that this multiverse that we are talking, where I explain a few of these things, can be even farther extended when we deal with repeated measures. And we just had that question before. So I have repeated measures. Can I add to my repeated measures, that's just kind of like a multi-trait? Depends on how you model it. Spatial analysis, yes, you can. Can I add to my repeated measures multi-trait? Yes, you can. It's not going to be easy, but you can. Can you add multi-environment, multi-trait to my repeated measures? Yes, you can. But again, so as you can see here, the possibilities are there to put everything, but things have to be done in a very careful way. You are demanding on the system, lots of variance components. You need starting values. You obviously need to clean the data very carefully at the beginning, and then start thinking about what units are the ones that are correlated, what units are the ones that are not correlated, and so on. And the factor analytic, it's a very good approximation, and it's a very good tool to model these multiple correlations. It's not exactly a US or a CORGH, but sometimes you can get to all the dimensions. Sometimes it's not worth it, but then it gives you that nice interpretability. Okay, I'm going to stop here. Again, you can always, there's a few more resources here, older webinars, some manuals. We have also short course if you want to know something about more ASReml that will give you a little bit more ideas. So have a little look. And again, if you need help, you can always contact us or contact me directly. So I'm going to leave this on a little bit. So do we have some questions? I have a few minutes to answer.
Yes, Salvador, we have a couple questions. So one of them would be, how can we handle a situation when some of the location have spatial information and others do not?
So that's relatively easy. So for example, notice here that I put a trait 1 and a trait 2. So you can have, for example, that's pretty much what I did before. I said trait 1 has no spatial information. And that's okay. That is, you just eliminate it. That means you're not extracting some spatial component from that trait. So the use of the at statement is very handy in that sense.
All right, thank you. And also, could you explain how to choose the most appropriate correlation matrix structure for your data?
So normally I go for the factor analytic, which is going to approximate to a CORGH or a US structure. I will say it's very difficult when you're dealing with multi-traits to go to a more simplified version. So for example, you can think, oh, why don't I try the CORGH? The CORGH assumes that the different, so imagine you're dealing with 4 traits. The different variances represents the variances of different traits, which is fine. But now the correlation is common across the traits. And that doesn't make too much sense because some traits might have negatively correlated, some are going to be more positively correlated. So in reality, you don't have, when you do multi-trait, you don't have much flexibility. You have to aim for a CORGH or a factor analytic. And if you only do multi-environment, yes, you can simplify it and you can say, yes, the correlations are going to be very similar. Remember what happened with ear height? They were all around 0.9. So maybe that will be a case where I only analyze that. You can always use a likelihood ratio test also to compare models, okay? So hopefully that answers your question.
All right, thank you. Do you have time for more questions, or maybe we do?
Yes, you can bring one more.
So there are a question when you have a multi-environment analysis. So you want to select the best varieties for each location, but at the same time, you also want to select the best varieties overall. So how would you make this decision?
So the software will allow me to have the predictions of combination of genotype group, which will allow me to, for example, in this analysis, to have a ranking of each genotype on each environment. And also you have a ranking of each genotype across all the environments. So how do you make your decision on which one is more appropriate or not? Now, personally, if the genotype by environment correlation, so this type B correlation, is higher than 0.7 or 0.8, you can think that you don't have too much G by E. And in that case, I will tend to use a genetic effect across all the environments. When the correlations are lower than that, that means you have relevant G by E, and you have to decide in your breeding program if it's worth to have productions or selections for different environments. Sometimes commercially it's not justified. Sometimes it is justified commercially. So you have to kind of come back with that decision. However, when you use you often see sometimes genotypes that are very stable. So they are the winners. And even though there's a strong G by E on your analysis, the winners tends to be very consistent and the losers tend to be very consistent. So you can eventually end up selecting individuals that are more stable for a system that has a strong G by E. But that's a question more for breeders. How do they decide and so on? I'm just giving you a few hints. Okay?
All right, thank you very much, Salvador. That was very interesting. And I would like to thank everyone for joining us today. We will be sending the recording to you in the next day or two. And any question that wasn't answered today will be answered and sent along with the recording. So that's it for now. Enjoy the rest of the day, everybody. Thank you.
Bye-bye. Thank you very much.